thank you, Daniel. We're going to talk about how semantic web technologies compare to TypeDB. The purpose behind this talk really is that because we have a lot of people within our community that come from a semantic web background, others that are interested in the space and generally want to know our philosophy when it comes to building product, specifically building TypeDB, and how that compares to what others may be familiar with. So largely, we're going to be looking at certain semantic web standards and comparing that to TypeDB. Now, before we get started, I do want to give a slight disclaimer, I guess you could say, to this talk, because we are comparing one technology to what effectively is a set of standards, and both of which also try to do very different things. The semantic web is for the internet, and TypeDB is really built as a closed world production operational database. So the comparison in many ways is actually very unfair to both technologies because they both try to do different things. Nonetheless, it's still very helpful to look at how the different approaches compare, especially when it comes to modeling data. And that's especially what we're going to be focusing today. So now, what the structure for this talk specifically, we're going to start with a high-level comparison, and then we're going to look at a number of standards and how they compare to TypeDB. So we're going to look at RDF, SPARQL, RDFS, OWL, and SHACL. Because of time, we're of course not going to go deep into each standard itself. We're going to touch the surface and really try to at least share some of the philosophies that we have implemented within TypeDB, just to make sure that you understand how those at a high level compare to those in those from the semantic web world. So first, to start with the famous semantic web standard or architecture. Now, of course, we haven't yet built out as an industry all of them. And for today, we're going to be focusing specifically on these ones, specifically the SPARQL, OWL, RDFS, RDF, XML, and URIs. And the first thing to note when we look at TypeDB and we consider how does TypeDB compare to semantic web standards, the first thing to really take note is that when we approached building the software, is that there's a lot of complexity inherent in the semantic web stack. It allows us to do an incredible amount of things, but that itself introduces a lot of complexity. So what makes that complex? Now, the short answer is that not only are there many standards out there, there's also a lot of implementations of those standards. Whether it's commercial, whether it's open source, academic, whatever. If you're new to the field, if you're building an organization and you're recruiting for people that can build software, finding these people can be hard because there may be so many different standards to learn about. And again, while they may be insanely expressive in what they can achieve, the learning curve can be very, very steep. And so what we built with TypeDB is a software that in the most fundamental of ways does what you need to do when you're modeling and working with complex data, what a semantic web architecture will try to do. Now, the important thing here is to note, or actually the analogy that we like to make, something that we take to heart when it comes to building product with TypeDB, is that if you consider the semantic web world as a do-it-yourself computer, where you can define your motherboard, your memory, a lot of the low-level architecture, a lot of the low-level components that you can tweak. With TypeDB, what we say is that we close that up, and instead of being a do-it-yourself computer from the 70s, TypeDB is effectively like a Mac. What that means is effectively you can't now choose your motherboard, you can't choose your processor, everything comes built in, but at least it works. And most people that are not familiar with semantic web technologies can actually use the software to and be successful with it without, again, the steep learning curve of certain semantic web technologies. So in that sense, TypeDB provides one technology as a higher level abstraction over semantic web technologies. So now let's start with the first standard that we're going to cover today, RDF. So RDF as a triple is something that I'm assuming everyone in this call is familiar with. We would consider a subject, a predicate, and an object as being in one as effectively as a predicate. The equivalent model, or effectively the underlying model within TypeDB is that of an entity relationship model. Well, we've got an entity, a relation, an attribute, and then we also have the concept of roles that defines how a thing plays a role inside of a relation. But we're going to come back to that in a second, because first, if we look at an example here, where we say, if we want to model that Peter Parker knows Aunt May, if we're represented in a triple, we could look at something like this, where we've got a person node with a name, Peter Parker, another person node with a name, Aunt May, and effectively a predicate knows between those two nodes. Let's say we then use the friend of a friend namespace to take the resources from there. The equivalent in TypeDB will be something that may look very similar, but it's actually very different. Because rather than thinking here in terms of edges, predicates, subjects, objects, instead what we say is that instead of triples, TypeDB implements a concept level entity relationship model. And so conceptually, when we're modeling here, we're saying that we have a person entity. A person entity has an attribute of type name with the value Peter Parker. That person entity is connected to another person entity through a knows relation. And that person entity has an attribute, again, of type name with value Aunt May. And because, of course, TypeDB doesn't actually work on the internet and is not built as a semantic web technology, there's no such inherent thing as effectively as a public namespace. And something that is not shown here is actually the ability to model roles, which would effectively constitute how something, in this effectively a person, plays a role inside a knows relation. But we're going to come back to that. If we look at how this would look in code, if we're using an XML serialization, and we're going to also look at something more simpler like Turtle, this is what it would look like on the left, and on the right is the query, is effectively the pattern in TypeQL of how this particular pattern would look like. We've got a person that has an attribute, Peter Parker. We've got another person, Aunt May, and both are connected to each other through a relation of type knows. Now, if you wanted, however, to model namespaces as or URIs to each individual thing, then of course you could do that. One of the things, as a side note, but something perhaps important for people coming from the semantic web world, is that anything in TypeDB, and by anything I specifically mean relations, attributes, and entities, anything can have an attribute, or actually what I mean is a first-class citizen. That means that not only can entities and relations have attributes, even attributes can have attributes. So now, and then we get to the concept of hyperrelations. So now, while in RDF, an edge is just a pair of vertices, a hyperedge is a set of vertices. And that has huge consequences to what we can model in the software in TypeDB versus elsewhere. So first, we have on the left here, we've got a ternary relation. We've got three things playing a role in a purchase relation. So we've got a buyer, we've got a seller, and we've got a product, all of which are in a purchase relation. So those are three things in one relation. You cannot do that natively, at least not representing that purchase relation as an actual relation in normal semantic web, in the standard RDF and RDFS. And then we've got nested relations on the right. Here we have a marriage relation between two spouses. But then let's say that marriage happened somewhere, and we want to refer that relation to another city through another relation. So we don't want to model a ternary relation here. We're saying that this marriage is effectively modeled as playing a role in another relation, a relation that we call located, that's connected to a city where that relation may have happened. And another example of a hyperrelation is the one you see here. So we've got a person entity, Bob. Bob here plays the role of husband in a marriage relation, where Alice plays the role of wife. We also have a divorce filing relation. Unfortunately, Bob and Alice are divorced, because Bob plays also the role of respondent, where Alice plays the role of petitioner in that divorce filing relation. And then we have the marriage relation that plays the role of certified marriage in that divorce filing relation. As we can see here, Daniel, Alice, Bob has not been lucky because Alice has requested a divorce. Now, while that may be not so cool for Bob, it's a pretty cool model, because we have here both a nested relation as well as a ternary relation. And so this is where it gets really cool to model with TypeDB, because we can represent these concepts natively without having to reify our model. Because if we're trying to do this in RDF, well, there may be other ways of modeling this, by the way. This will be just one implementation. The point is that there isn't a native way just in RDF to model this directly, without whether it's a plugin or perhaps effectively reifying your graph, which technically can work, and maybe that'll work for you. But reifying your graph is still effectively changing up the model in ways that aren't actually naturally accurate. So it's very important. So it's important to say that in TypeDB, hyperrelations are first-class modeling constructs. Now let's look at some other modeling constructs. For example, higher order relations. Let's say we first have a statement that says J.K. Rowling wrote Harry Potter. We may represent that here in Turtle as Harry Potter author J.K. Rowling. And then let's say we want to make a statement about that statement. Here we say that the book was written in the year 2000. We can do that by effectively creating this node here that connects all of the different informations that we want to connect. To do this in TypeDB would look as follows. So the initial sentence of J.K. Rowling wrote Harry Potter can quite easily be represented again as a book connected to a person through an authorship relation. But then if we want to say something about that relation itself, we simply add an attribute to that authorship relation. And the attribute here that we add is of type date with value 2000. And then sometimes we get the question as, how do we do blank notes in TypeDB? Well, firstly, the short answer is that there's no such equivalent thing as a blank note, simply because TypeDB doesn't work with incomplete information. By default, as far as TypeDB is concerned, whatever data is in TypeDB, it is complete by nature of it being a closed world system, versus an open world system where we need the concept of blank notes to fill in some of the gaps. But if we were to make a comparison, let's say we've got a sentence that says Harry Potter was inspired by a man who lives in England. A blank note could perhaps be represented as effectively a variable with less information about the type. For example, $M here on the right represents just the type man without any further information. Or the equivalent would be to query for a thing without a key URI if you have modeled it in TypeDB in that way. So having looked at RDF, let's now consider also SPARQL. SPARQL is we can start by looking at how to insert data into SPARQL. So let's say we want to insert the following statement. The statement reads, a book with the title new book and creator and other. I don't know how many times I've said this, but I think that's pretty funny. So what this SPARQL query could look like would be like this. Here we've got a one namespace here, and we're inserting the data as we see here. And in TypeDB, we use the keyword insert to state that we're inserting data, but rather than thinking as effectively connecting something to a node, we're saying that there's a book that has a title and has a creator. In this case, we're representing both of them as attributes in this example. So how do we query for data? Now, to answer the question here, who are all the persons that Adam Smith knows? So this is a more interesting one here in SPARQL, where we're specifically interested in the variable whom here that is connected to Adam Smith. But in TypeDB, what we could do is first representing the person that has family name Smith and given name Adam. And then we say that $P is connected to $P2 in a knows relation. And because we're just interested in getting $P2, which is undefined, we haven't said anything, any type information about P2. We specifically want to fetch for $P2. And that's why with the keyword get, we simply fetch for get $P2. And a more complex query, give me the director and movies that James Dean played in, where also a woman played a role, and that woman played in a movie directed by John Ford. It's a bit more of a mouthful. And in TypeDB, the equivalent would be the following. Now, I would direct your attention to a couple of things here. The main thing being is that some of these relations, we specifically define the roles, the role players in. And in particular, the relation on this line right here, where we effectively create a ternary relation. There's three things in one relation. This is a relation of type casting, but we've got an actor that is played by the man James Dean. We've got an actress that is played by a woman that is undefined, or at least not filtered. And there's a casted movie that is $M. And $M can be anything. We haven't actually declared what that type is. And at the bottom, we get for the information based on the traversal that we've defined and the filtering that we've done as well. And conceptually, we also want to highlight how we would think about this query if we think of it in graphical terms, because the SPARQL query would look like follows, whereas the TypeQL query would look like this. And we use an entity relationship notation to denote the relations, denote the entities. That's our preferred way. And then also the role names that we add to each of the things that are connected in a relation. So here we've got that ternary relation that I mentioned earlier, where James Dean plays the role of actor. The movie is playing the role of casted movie, and the woman's playing the role of actress. And then we get the rest of the traversal. But again, very important to note here, we think in terms of entities, relations, and attributes, conceptually, in other words. So with that in mind, let's look at RDFS. Now, the RDFS is, of course, just a beefed up version of RDF with more schema and ontological functions, starting with the ability to subclass. So let's say we've got an animal, and we've got a subclass horse of animal. In XML, it would look like so. Versus TypeQL, we could define it simply like this. So using the keyword sub, we would declare in our schema. So right now we're looking at the schema language. Before we were looking not at the schema language. And the schema language here shows us that an animal is a subtype of an entity, and a horse is a subtype of an animal. So we're saying that all horses are animals, but not all animals are horses.
One could argue that my dog is both dog and horse, given how large he is.
Whoa, okay, fair enough. We do not support, however, multiple inheritance. So, but we'll get there. We'll get there in a second. That was a good transition, Daniel. So now beyond just entities that we can subclass, we can also subclass relations, and we call them subtyping rather than subclassing. So subtyping of relations is, again, simply using the keyword sub. Here we say employment subrelation, and let's say there's different types of employment relations. For example, a part-time employment relation. Again, using the keyword sub, we can simply say part-time employment, sub-employment. That gives us the model that we're looking for. And this is where your transition comes in. Now, Daniel argues that his dog is both of type horse and of type animal, right?
But it doesn't quite sound right conceptually.
Well, you're trying to inherit from two parent types.
Right.
That's not possible in TypeDB. And firstly, it's incorrect,
right?
Biologically. Yeah. However much
a small child could ride on the back of my dog, but that's for another time.
I don't think the writing defines whether something is a horse or not.
No, you're right.
So, but the point here that we're trying to make is that multiple inheritance by definition, by philosophy, we don't support that. And I'll tell you why. So let's say, and I'll explain by way of example. So let's say we've got a class employer, and the class employer subclass is a subclass of company and government. And we can, in Turtle, we can represent this like this. Versus what we would want to do instead in TypeDB is use rules. That's roles with an O, not rules. Because roles, in most, if not all cases of multiple inheritance, are actual use cases of doing composition using roles in TypeDB. So what we're saying is that if we've got a company, rather than thinking of it as a subclass, effectively subclassing it, having an employer, we simply say that the company or government only plays the roles of employer in the context, only in the context of an employment relation. So the example here of multiple inheritance, in our view, is wrong. And defining those definitions for what can and what cannot be modeled in what roles can be played is done like so. So we've got an employment, a company that plays the role of employer in an employment relation, and simply we see there at the bottom, and with the keyword relates, we can then define that the role relates to a particular relation. So this is an important point. In TypeDB, we support single type inheritance. And TypeDB prefers composition over inheritance through roles. Now let's look now at RDFS domain and RDFS range. Again, those constructs natively don't exist in TypeDB because of the difference in product philosophy. First, domain, but those use cases can be modeled in different ways. For example, if we wanted to represent a type of domain here, of RDFS domain, for example, if we were saying that if someone has published a book, we want to attach to the class published book, then rather than thinking of it as giving it a class, we give it a role. So here we can create a rule that effectively mimics what RDFS domain is trying to do. So if something has a published date, any published date, then it must play the role of published book in a publishing relation. And similarly, we can have range here. If we say that if someone is a member of the house brother predicate, the value, then it must be a member of the male class. We can do the same effectively by saying that in a TypeDB rule, that if someone plays the role of brother, that it has the gender male. And we would rather represent this as an attribute rather than having it as an entity or as a class. So let's, in a more elaborate example is that if we have, let's say we have a vessel of class departing vessel, which has the property next departure specified, we could state the following. We've got a Queen Elizabeth II, that's a vessel that it has as its next departure March 4th, 2010. With RDFS domain, any vessel with next departure will be inferred to be departing vessel. And this will mean that Queen Elizabeth II will now be a member of the departing vessel class. So in TypeDB, we could write a rule that connects any entity with a next departure attribute to the departure vessel role. And that would look like so. And so now if we insert this data, a vessel with the name Queen Elizabeth II and has next departure March the 4th, 2010, TypeDB will infer that Queen Elizabeth II plays the role departing vessel in a departure relation. So now moving to OWL, let's look at a few of the axioms in OWL and see how they could be translated into TypeDB. Again, it's important to note that TypeDB doesn't actually provide an ontological reasoner. The type of reasoning that TypeDB does is a rule-based one. And so a direct comparison between the two needs to take that into account. So let's say we're looking at this restriction called all values from, that where we want to say that the range of has parents with a person or animal class can only have person parents or animal parents values. Because even though Daniel considers himself to be the father of his dog, he's actually not the biological father. Oh, unfortunately. So this restriction would look like this in Churchill serialization. And that same restriction, we would model that in the schema of TypeDB. So what we're saying is that we've got a person type that plays the role of child, but in a person-parentship relation. And the same for the parent. We do the same in an animal, but then we create this animal-parentship relation. And at the bottom, we see that this person-parentship relation and animal-parentship relation, both of those, they inherit. They are subtypes of the parentship relation, which is an abstract type. So now if you did want to query for all the parentship relation, we can still do that. But at least we've modeled it in a way that guarantees that, that an animal, that Daniel cannot be the biological father of his dog. And so that guarantees safety at the database level. And then we can look at transitive properties. So let's say that if A is connected to B and B is connected to C, then A is also connected to C. So transitivity can be implemented like this in Turtle. And in TypeDB, we would write a rule that simply states that if A is connected to B and B is connected to C, then logically A must also be connected to C. And this will always be true in a deterministic way. And by the way, these rules are represented as part of your schema. So with this TypeDB rule, if we now insert London connected to the UK, or London is located in the UK, and if the UK is located in Europe, then this query will return also London, besides just the UK. So even though London isn't directly connected to Europe, it would still return the right result. So here we can look at equivalent properties. So here where two properties have the same property extension, where we say that we could say that this borrowing relation, if that one exists, always also create this other relation type checked out. To make it more interesting, we can of course actually also add qualifiers to the when statement. It may not be, I think, necessarily anymore an equivalence relation, but I hope you can understand that we can add a lot of logic to these rules, and they will work at scale in production or at any point in time. Now, let's say if we want to say red wines should have the color red property, this can be shown like so in TypeDB, in OWL. And in TypeDB, we could simply say that if there is a type called red wine, they must also have the attribute of type color with value red.
And that's an example of a rule in our in TypeDB schema.
This is a rule in TypeDB. Yes. So a final note a little bit on SHACL. Now, not too much, just because in terms of time. So now, if we want to do verification with SHACL, schema-like constraints, let's say we want to restrict a person that can only work for a company, and we want to restrict a company to have a name attribute of the data type string. We could do this like this in SHACL. And again, these types of restrictions go directly into the schema file, the schema in TypeDB. So here we simply say that a person can play the role of employee, but only in an employment relation. The company can play the role of employer, but only in employment relation. And at the bottom, we've got the attribute name that must be of value string. So to take a step back, because we've looked at it quite a lot, in short, we say that TypeDB reduces the complexity while maintaining a high level of expressivity. We provide a higher level of abstraction for working with complex data. And ultimately, when we look at the semantic web, well, as the name suggests, semantic web standards are built for the web, whereas TypeDB works for closed world systems with private data. So considering both approaches, when we look at TypeDB and the approach that we take to building the product is that TypeDB provides one technology as a high-level abstraction over semantic web standards. So with that in mind, thank you very much for attending. Feel free to reach out if you have any questions. I think if anyone is based in London or in any of the major cities where we do our meetups, hopefully soon we'll be able to come to you and to organize some great events and some beers after or tea, whatever you drink afterwards. So if there's any questions, happy to.
Absolutely, and thank you, Tomas, and good shout on finding your local meetup. I did drop that link here in the chat, and I will just, for those that joined at the last minute, that's not right. I want to drop where you can find all of our meetup groups. And there was a question here. Are there any particular guidelines or a process a la RDFS normalization for modeling in TypeDB?
There's some information online in documentation. What we generally advise, if you go about the normal, effectively ER diagram modeling, the conceptual model is the direct model that we implement in our code base. Now, some of the advice that we can take, especially if you're working in a new model, is thinking what are some of the high-level questions that we want to answer from your data. Let's say there's 10 questions that we want to answer, and then work backwards. What are the entities? What are the relations that I need in order to actually answer that data? Then you can look at what's the data that I actually have available and see how that matches to the model that you've created. May mean you need more data, and you have to gather that. But starting with 10 questions is a good way to at least get a sense of the value that you could get from TypeDB.
Yeah, it's a great tip. Great tip. So this is the moment where we sort of like to model or rather emulate the live meetup experience. So if you've got any comments, feedback, questions, ideas that you want to share with the larger group, find the raise hand button in Zoom, and I can demonstrate that. I don't know if you can see that or not. And we can bring you off mute, and you can share with the group. Otherwise, feel free to drop a question into the Q&A or into the chat. And we do realize that there is a lot to digest in just a 45-minute session. So please do join us on Discord. It's a great way for you to sort of begin to process all of this, and then you can pose questions there where the community is more than happy to dive in and chat with you. Let's see, SK says, can and how will TypeDB integrate open world knowledge bases, maybe those that are designed using semantic web techniques?
Well, the larger point is that you can't make a fair and just one-to-one mapping between those models. So so if there are certain open world knowledge bases that people want to use within TypeDB, then we would want to create those models in the first place. And so that requires whoever is in charge of those projects to build those models. So the question, can TypeDB represent those? Yes, definitely. One way is just to directly import everything into TypeDB. But if you want to, if you're going through the effort of actually pushing it into TypeDB, I insist that we think, how could we model this in a better way, and then ingest the data, because that really would justify actually using the TypeDB software in the beginning. Again, the larger point being is that most knowledge bases based on semantic web technologies, because they're based on semantic web technologies, the TypeDB model is literally a higher level model than something lower level. So we want to actually make use of those higher level constructs by rethinking our model, ideally.